I see. Thank you. So let me start with the definition of causality. The definition of causality could be a bit tricky, and normally it's thought to be like no time machine is allowed, so we cannot go back in time. But what does it mean really for the physical theory, which normally we thought to be like we don't know the full theory, we know only infrared theory. How can we check that some particular theory is causal or not? There is a simple way of doing that, is to compute time delay of the signal propagating on top of background and compare it to the signal, to the propagation on top of the propagation between, without background. Here we mean by background we mean that there is some field background, not obligatory gravitational and not curved space, but just some fields, classical field background, like electromagnetic field or so on. And then if one imposes a strict causality condition that we always must have only time delay, then apparently this condition was shown to be too strong because it will rule out all higher derivative terms. Like it was shown in the paper by Kamanho, Edelstein, Madasena, and Zhibayev.
If I understand correctly, this shows that we have to have higher spin tower in order to recover strict causality.
Well,
if you have high derivative correction, time advancement appears beyond some UV scale.
Yes, but well, the point is that maybe in specific UV completion you still can reconstruct causality.
Yes.
But
so you are talking about when you truncate.
Yeah, I'm considering truncated theory.
Okay.
But then, of course, I have to limit myself when with smooth enough backgrounds and propagation, also some constraints on propagation energy, on the energy of propagating particle, because I cannot describe anything. So yeah, we are speaking about truncated effective field theory. And here there is a picture from a plot from our paper showing explicitly what's happening in a truncated theory. That's in this plot we show two coupling constants appearing in effective field theory of photons. Actually, it doesn't matter. Well, just to show the result, it doesn't matter what is their meaning. It's dimension 6 operators. But these 2 points are known UV completions, known partial UV completions, like axion UV completion and scalar UV completion. So these points should be within the allowed region. Otherwise, it's a little bit strange to have to forbid having explicit UV completion, which can be just constructed, and the particle can be integrated out. Apparently, we have shown that we need a weaker condition. It was known sometime before that, in principle, a weaker condition makes better fit to the condition corresponding to analyticity of the amplitude, so to Boголюбов causality condition. But we checked explicitly by comparing causality constraints that this condition is more relevant. So this condition consists of the fact that we allow small causality violation, which corresponds to unresolvable time advance from the point of view of quantum mechanics. Energy time uncertainty relation, and if delta t, if the time delta t time advance is smaller than 1 over omega approximately, then we cannot resolve this kind of time. We cannot decide whether it's time delay or time advance from the point of view of quantum mechanics. So this small micro-causality violation will not sum up to a large time loop, time-like loop, which will break causality and which would allow to build time machine. So this kind of condition still guarantees that we are safe in the sense of having no time machine and going to the past. Here we have a concrete set of numbers standing in this relation, and we can see that in the plot where there is a strict causality condition implemented. That's the dark blue plot, dark blue line here, and it doesn't. It's not consistent with the line between axion and scalar UV completion, which must be inside of the relevant region. So this is too strict.
By axion UV completion, you mean axion photon coupling?
It's not full UV completion, of course. It's again non-renormalizable, but the scale of, I mean, you can integrating out the axion, you get terms proportional to 1 over mass of the axion. But in the axion theory, you can have a higher scale, much higher scale, where it becomes non-renormalizable. So partially for the between the mass of the axion and the scale in this axion theory, you have partially completed theory in this sense.
If we say the regime of validity of EFT, you have time advancement. This is what we're saying.
Yes. So we are all these computations were done as one of the important requirements was that we stay in the validity regime of EFT. So and then allowing for time advance of order unity, we get this line to be inside of the region which is allowed by causality. Okay, so yeah.
Is omega a frequency of photon?
Yeah, omega is a frequency of photon which is propagating on top of some electromagnetic field.
In this figure, you fix the value of omega. Did you fix the value of omega?
No, value of omega here is not fixed. The computation here is a bit more complicated in the sense that we studied propagation of signal on top of background, and it was like really hard work done by Marianna, by my collaborator Marianna, who numerically was adjusting the background such that the best bounds are obtained. So the background was adjusted in such a way that the strongest bounds were obtained in each case. So this figure appeared as a result of quite complicated numerical procedure of optimization of these bounds with respect to the background choice.
Oh, yes.
That's what was done. So omega here, yeah, omega here was also a parameter of optimization.
I see.
The purpose was to have only some region allowed in terms of dimensionless constants. That's one of the examples of causality bounds, and the purpose of our work was to compare them to the other definition, to positivity bounds, in fact. So let me define this framework and what is positivity bounds, what we were looking for. So in general, we consider effective field theory valid in infrared region, where we can have some expansion also with a lot of higher derivative operators, which are becoming more and more relevant once we're approaching here. Here we have something which we don't know, and in the UV we also should have some theory, but we don't know which. Maybe it's string theory, maybe not, but we assume some properties of this theory. Then positivity bounds, in fact, would be derived if we assume that UV theory is local, unitary, and all the scattering amplitudes are analytic, which corresponds to Bogolyubov causality definition, which is kind of a little bit different than direct causality check. So we compared direct causality check, like just classical propagation of signal, with a more involved thing like quantum causality condition coming from the analyticity of amplitude, which is directly related to analyticity of amplitudes. So these are our assumptions in these frameworks. In this framework, in general, assumptions about UV will give constraints on IR theory, and these constraints are called positivity bounds. I'll show the derivation of some of them a bit later. And also, and this is very much related to the work by Toshi, infrared results may require special UV properties for their consistency. And that's also, I will refer to that at the end of my talk when I introduce gravity contribution to positivity bounds. The symmetry working in IR and UV in both cases can constrain the structure of infrared EFT, and that's very relevant when we are just writing all the terms which are allowed in the Lagrangian. Say if it's a scalar field with a shift symmetry, then we have a constraint not to write any other terms. So positivity bounds are derived from assumption that the UV completion is good enough. What do we mean by good? First of all, it's Lorentz invariant, and for amplitudes, it means that it should be a function of 3 Mandelstam variables. Another condition like of being good is unitarity. Imaginary part of the amplitude should be positive. Causality, by Bogolyubov's definition, will lead to analyticity of the amplitude everywhere except real axis. And locality is more subtle property, which actually transfers to polynomial boundedness of the amplitude, which is called Froissart-Martin, from which one can derive Froissart-Martin bound. For strictly speaking, this is a bound for gap theories for scattering of massive particles. In this case, it can be derived from polynomial boundedness. But often, but we also will assume that similar relation is valid for massless theories too, maybe with weaker condition like amplitude should be smaller than S squared. But this bound for for theories with massive particles without exchange of massless particles can be just straightforwardly derived from a condition of polynomial boundedness. So why we call it positivity bounds? In the simplest positivity bound could be derived in the forward limit of the amplitude. We take t equal to 0, and then we know the structure of the amplitude, the analyticity structure of the amplitude as a function of S in the complex plane. It can have only poles in the real axis and 2 branch cuts from forums, from the cut where you start kind of real particle creation in this scattering, and the opposite cut for negative S. Then this and everywhere else the amplitude is analytic, and this property allows us to use complex analysis to get non-trivial relations between infrared limit and ultraviolet limit, in fact. So if we construct a quantity which is called here sigma r as the integral over a small contour gamma of amplitude over S minus mu squared over 3, where mu squared is chosen to be here inside of this contour. Then from the one side, it can be computed only within the knowledge of effective field theory. Apparently, it's just a second derivative of the amplitude in the point mu. So it's not S, but mu here. But the other this contour also can be mapped into two branch cuts and infinite contour around infinity. Given that Martin-Froissart bound is satisfied, this infinite contour is just equal to 0. That's why we choose power 3 here, because it's the minimal power which leads to infinite contour, which allows us to throw away infinite contour contribution. And then it will give us some of imaginary parts of the amplitudes of the kind of scattering amplitude, and it's crossed symmetric one. And the main observation here is that this expression is always positive if imaginary parts are positive, which is an implication of unitarity. So then we conclude that second derivative of the amplitude should be positive, which is already a non-trivial constraint on effective field theory. So what to do with massless particles? It's more involved, but still one can deal with that. One of the ways we used in our paper with Mario Herrero-Valea and his PhD student Raquel Santos Garcia, we introduced a point mu to be not here, but in a complex plane. We shifted it a bit to the complex plane and also derived the same relations. With positive right-hand side, we got the same, actually the same Wilson coefficient in the FT to be positive. So in practice, at least for scalar particles, having them massless doesn't change anything in derivation of positivity bounds. Even though formally this contour looks a bit different, these two branch cuts are merged into one, and the complex plane becomes split to two. So further advancement that we used when computing positivity bounds for photon EFT is connected to the possibility to obtain nonlinear, to have more bounds, to obtain nonlinear bounds for the Wilson coefficients, and positivity says us that just some Wilson coefficients are positive, but sometimes we may want to have extra bounds, like bounding not only the sign of the Wilson coefficients, but also their size. And this can be derived, for example, from Cauchy-Schwarz inequality. Recall that this is an inequality for any vectors. It can be also written in its integral form. So it's like square of sum is less than multiplication of two sums. And this can work also for integrals through which the amplitude, the derivatives of the amplitude can be expressed. Here we use another approach, take not a point, but take integral of derivatives of the amplitude, also including t derivatives in the limit of t going to 0. And we compute the quantity which is integral over this arc, and express integral over this arc through integrals over two branch cuts here. These kind of arc integrals are more convenient when applied to theories with massless states. So derivatives of the amplitude can be expressed through this kind of arc integrals, and these arc integrals can be combined in such a way that they form Cauchy-Schwarz inequality. So one of the simplest cases, which can be directly applied to theory of photons, but doesn't bring anything new for scalar theory because it's fully cross and symmetric. One of the examples is that integral, expressing third derivative of amplitude square should be smaller than integral of second derivative multiplied by the integral of fourth derivative. And this integral relation will propagate into the condition that third S derivative of amplitude squared is less than second derivative multiplied by fourth derivative. This is the simplest thing which can be derived in Cauchy-Schwarz inequality. In our paper, we derive another important inequality, which is a bit more complicated since it requires some work because some terms are becoming negative, and you need to take care about getting the proper signs everywhere. So we found this inequality, and then
symmetry.
Actually, scattering amplitudes of photons there will be 3 independent amplitudes with respect to different scattering of different polarizations, and some amplitudes are explicitly crossing symmetric, so you can exchange TS and U. But some of these amplitudes are not crossing symmetric. But when you do crossing symmetry, you also exchange the polarizations. And in this sense, it's still crossing symmetric, but not like if you take partial amplitude, it will look non-crossing symmetric. So third derivative with respect to S will be non-zero for these parts. So let me come closer to the theory which we actually studied. It's photon EFT. It has we studied like dimension 4, dimension 6, and dimension 8 operators with Wilson coefficients in front of them. There are only 2 dimension 4 operators, 3 dimension 6, and 3 dimension 8 operators, which give non-trivial contributions to the amplitudes. So, and that's 3 independent amplitudes which can be written, which can straightforwardly follow from this theory after some exact computation in Mathematica. And this is a relation between Wilson coefficients in Lagrangian and coefficients in the amplitudes. So this structure of the amplitudes, so you see that, for example, this particular amplitude is not obviously crossing symmetric. It has a S-cube term, and it will contribute to the inequality which I've shown before. So to make these bounds, the bounds stronger, we use not only nonlinear relations between nonlinear integral relations, but also do some analytic optimization with respect to choice of polarization. So these are 3 independent amplitudes, but in principle you can scatter any state, which is like a linear combination of these amplitudes, scatter it to linear combination of these amplitudes. And in this case, this can be parameterized through 4 angles, theta, phi, chi, and psi. All the combinations of the amplitudes which lead to, well, what is important here is that we are scattering only pure states of photons. We don't scatter entangled photons. This is reflected in the fact that the coefficients of the amplitude are kind of separated into the multiplication of these coefficients, but scattering entangled photons is not allowed for the reason that it will break crossing symmetry. You cannot, when you are doing crossing symmetry, you need to exchange also T-channel amplitude, and if the initial state was some entangled state, it's not clear how to make a crossing symmetric state. So this doesn't work for that. We are allowed only to consider so-called indefinite polarization scattering, and then that's our amplitude, which is a function of angles also, and all the bounds can also be checked against whether they are valid for all angles. And variation with respect to angles will make the bounds much stronger, and moreover, they will become compact. So we'll be able to bound not only signs of Wilson coefficients, but also sizes of these coefficients. And this is the set of bounds which we're actually getting. We've called them linear bounds and nonlinear bounds, referring to the linear positivity, linear dispersive relations, and also nonlinear ones. Already from linear bounds, it's more or less clear, for example, that we can optimize, for example, the first inequality with respect to choice of the angles, and get that, say, adjust angles in such a way that get F2 coefficient bounded between G2, minus G2 and G2. And given that these inequalities should be valid for any values of angles, they are kind of leading to compact constraints on all coefficients except the first coefficient G2. Actually, the first coefficient rescaling of the first coefficient corresponds to rescaling of the cutoff scale lambda in the theory. So once we fix the cutoff scale, the other Wilson coefficients are becoming likely to live inside of some compact regions, which are not very, which are bounded by numbers of order, normally of order unity, at best of order 10. That's one of our conclusions. And also nonlinear bounds contribute to this kind of structure of bounds on the structure of AFT, in the sense that we also get stronger bounds than linear bounds from that. And we found a way how to get part of these bounds analytically, part of nonlinear bounds in the sense that normally we have this kind of inequalities from linear bounds, and then optimization with respect to angles can be performed fully analytically, leading to the two very simple relations. Well, this one is extremely simple, and this is more involved because it's like a quadratic equation inequality. Then it's like a school level mathematics to study what are the bounds and these coefficients, given that the value this variable y is cosine psi, so it's bounded between -1 and 1. And in some particular cases, it's possible just to get so our bounds which we are getting are in fact apparently some four order curves in the space. Yeah.
This is how to say, the result of optimization.
This is fully analytic procedure, like I just solving problem when this is positive for all values of angles phi, psi, theta, and phi. And after some playing with trigonometry and quadratic equations, we arrive at this kind of bounds.
Is this how to say analytically? Sorry, I say analytically optimized, right?
Yeah. It's just this inequality, the requirement that it's valid for any angles. From that, it follows that this should be satisfied and this should be satisfied.
You can use by optimization phi and theta and chi.
Yes, you are just.
You cannot use psi.
Why? No, I have to do optimization with respect to all these four angles. In fact, so it leads to this. It reduces to this kind of two inequalities. You mean that here?
Yeah.
Here there is still cosine of psi. Yes. In fact, yeah, because the full result is a bit longer because it has like 4 different cases of these roots of this polynomial, quadratic polynomial, when they are falling into the region between -1 and 1, but they all can be written in terms of discriminant and all these values. Yeah.
So you mean it's better to not optimize about y?
No, it can be optimized. I just wrote it on the slides because the full procedure is like 4 different cases. I implemented it in Mathematica. It's not a big deal, but just showing it, it's not convenient. It's just lots of roots and cases, different cases. Apparently, you have different possibilities where this variable y, when the roots of this polynomial lie between -1 and 1. So that's our assumptions behind this is the positivity story, and I'll show plots or the bounds which we got. But we also, since we compared positivity and classical causality bounds, let me show this table where we compare our assumptions behind it. Because it's essential to understand why these bounds are a little bit different, why ones are stronger and the others are not so strong. So in causality bounds, we assume, both at causality and positivity, we assume Lorentz invariance as an essential property. It's both for in causality bounds, we don't care about UV completion because it's just a truncated theory. In positivity bounds, we must care about UV completion because we close the contour at infinity and we must assume locality of UV completion in this sense, traced into boundedness of the amplitude by s squared. Otherwise, we don't have these bounds. So this is important. Unitarity is implemented only in the sense of Hermitian Hamiltonian. We have all real Wilson coefficients in causality, but in positivity bounds, it's positive discontinuity of the amplitude. We require no resolvable time advance as a definition of causality, and analyticity of amplitude in the complex X-plane for fixed t as definition of causality in positivity bounds technique. And it seems that these two definitions should be equivalent, but not equivalent with the definition of no time advance at all. So we still must allow for resolvable time advance to fit with the analyticity bounds. Also, locality for causality bounds mean that we assume IR theory is local, so we don't allow some crazy operators like one over box. In positivity bounds, it's a bit stronger assumption because it's related to Froissart-like bound on the UV, which allows us to close the contours. And of course, we also have this local IR theory, but we also require that UV theory is local. And there are some assumptions about validity of signal propagation on top of background, like EFT and VKB expansions under control, that it's indeed a signal propagating. And background is generated by localized external source. We don't consider too crazy backgrounds. In this work, only spherically symmetric backgrounds were considered. And of course, we consider that infrared EFT is under perturbative control, and which in positivity bounds, this requirement corresponds to the fact that we never take this contour to go further than cutoff scale of the theory. So there is some value epsilon. We assume that it's at best epsilon is equal to 1, but not larger. So, and these are some fun plots which we obtained after dealing with these inequalities. Since we had recall that this is a photon EFT theory, we have 3 parameters here, 4 parameters here, and 1 here. In fact, this parameter doesn't contribute to the bounds we considered so far, so it can be as well, it doesn't contribute to causality bounds. So we do not write inequalities on G4 prime. Because in fact, it vanishes from all causality bounds, apparently. So we have some confined system of which bounds 2 parameters, because we can, in principle, fix the value of parameter G2 to 1, saying that this is our definition of scale lambda. So if we set G2 to 1, we have only 5 free parameters to vary. But still, 5-dimensional plots is a bit tough to construct. So we are plotting slices of bounds. These are just positivity bounds, and for dimension 6 operators, we get this kind of funny figure which bounds them. And this is how this figure is shifted when I vary one of the parameter F2 here. So this blue point is, I think, the scalar theory, and this red point corresponds to some spin 2 UV completion, which also lines practically in the boundary of this region. And these are positivity bounds for dimension 8 operators. We have just 2 of them, because the third operator doesn't contribute to causality and also to the subset of inequalities which we are using. So we can get some somewhat stronger bounds. These are UV completions, and here I vary the parameter F2. So sometimes this has the bounds have this form, and sometimes they are restricted just to 1 line. And in 3D plot, if I want to consider how this is the allowed region, actually the same figure as here. If I allow, if I'm making use of nonlinear inequalities, and here optimization was done numerically, because these are nonlinear inequalities. These inequalities are nonlinear, and they contain more combinations of angles. Then dimension 6 operators are squeezed between dimension 4 and dimension 8 operators. And here I use different values of dimension 8 operator, G4. And if I'm making it smaller, then this region reduces just to 1 point. So comparing to here, if we start comparing them to causality plots, then we have many different situations, in fact. And these are plots for F2, G3 operators, and this point and the slice is chosen such that this point corresponds to scalar electrodynamics. And this is spinor electrodynamics, so it's QED. This point is QED. And this point is vector charged particle, which corresponds to vector electrodynamics. So this UV completion nicely lies inside of both positivity and causality plots, but they are kind of go in a little bit different way. In fact, this means that our positivity bounds are not this can be easily explained by the fact that we are not using all set of positivity bounds. We use just several inequalities, but we do not go to higher order recent coefficients, which will after projection on may also lead to extra bounds after projection on the space of lower dimension operators. So the positivity plot should be smaller, in fact, than this one. That's our expectation.
I explain
Yeah.
again the difference of the three figures. So the dot in the figure is the QE, spinor QED UV completion.
Yeah.
And the second one is spinor QED. What's the difference of the axis? You have three plots, and I don't see the label of the axis.
The labels are G3 and GF2.
So you are looking at different coefficients.
Yeah, there are different coefficients. We have three plots because we took different slices of. So in order to make this point lying precisely in this slice, we had to fix other parameters to be corresponding to what happens if you integrate out electron. So we fix all others and leave free G3 and F2 and make this plot, make positivity and causality plot. So in general, we assume that causality should be a weaker condition because it has assumptions only about IR and not about UV. But here it's kind of comparable strengths, and we know that we use non-optimal positivity bounds. So it's not a contradiction. I mean, this region is not a contradiction to the bounds. It's a sign that we are to improve the bounds.
Yeah, for positivity we can further improve by taking it about higher order terms, etc. And for causality bound, can we improve?
I think we can, but in fact, maybe it requires spherically symmetric backgrounds, which I'm afraid is very complicated. I think it's possible, but the program which Mariana was dealing with to obtain these bounds was already really complicated already for spherical backgrounds. So I don't know if it can be improved further. At least it can be whether it can be easily improved further. But for G4F4 plot, we have a nice coincidence between positivity and causality. And also with the statement that causality is weaker. What happens is that positivity allows bounded region from upper region, but causality allows the full cone. It can be valid, and it seems that for causality, in this direction at least, these bounds are not compact. Causality bounds do not lead to anything compact in this direction. So this whole cone is allowed. So how much time I have?
I think 10.
10 minutes, okay. So the whole cone is allowed, and probably it's connected to the fact that locality is not constrained in the UV for this method. So it should be some non-local series living here. But there are some cases where causality, especially for dimension 6 operators, leads to very strong constraints. And apparently, it's only one point, which is this is a remarkable plot, where just one point is allowed by both causality and positivity. This point corresponds to scalar UV completion. So it looks still consistent, but it shows that we must improve positivity bounds such that they will reduce to 1 point. And causality says us that we must do this reduction. And here these bounds are even not crossing, but it's okay because they can just in extra dimension, if we plot extra dimension, then just this point is not allowed. That's fine. On this slice, it's not allowed. Yeah, that's another thing, how it happens with extra dimension. So this is allowed, the blue region here is allowed by causality. This line is from axion to scalar, must be allowed as having, as we know, UV completion. And this nice figure shows what happens because positivity now restricts in a different dimension. Positivity allows only one line, and the region allowed by positivity goes in third dimension here, in another dimension. So this is quite tricky, and that's another point where just some random picture how it happens. Sometimes it's one plot, but rotated in different, seen from different points. And blue point is UV completion, so it's always allowed. So, I mean, if you look at from different directions, you see absolutely different pictures from the point of view of coincidence between the bounds. Let me make a brief summary of photon bounds and go to some results with gravity. Indefinite helicity scattering provides stronger bounds on EFT of photons because we can do optimization with respect to polarizations. Causality is a condition independent on the assumptions about UV completion. So in several plots, we see that it's weaker than unitarity, and moreover, it doesn't lead to compact bounds. And some regions naively allowed by unitarity correspond to a causal propagation, but which means not a contradiction, but just the fact that positivity bounds can be improved further. And let me switch to dispersive to what happens if we switch on graviton exchange, because it makes it much more tricky. This, in fact, we didn't consider graviton exchange at all in our studies of the photons, and I will explain why it will make things different. So if we have graviton exchange, we have the following structure of divergences at tree level and one loop term. And in the dispersive relation, if we take second derivative of the amplitude, we see that it's divergent when t goes to 0. So it's a bit tricky how to implement a dispersive relation and get positivity bound. But it can be turned into the fact that we can actually find the UV limit of right-hand side of the amplitude, of the imaginary part of the amplitude. The only source of divergences is in the left-hand side can be an infinite tail of the integral. And this infinite tail of the integral, we can look at that as some integral equation on the function on the imaginary part of the amplitude and try to solve this integral equation. One can guess the solution for reproducing 1/t pole, and it was done in the paper by Takuda, Aoki, Hirano. So this kind of so-called Ricci behavior will reproduce 1/t behavior in the amplitude. And in our work, we did the same for log t term. We found this term that it should behave like some parameter over logarithm of s. So this should be the amplitude for s, where s can be even larger than Planck scale. So we somehow get into the region where s can be very large and t when t is still small. and reconstruct the amplitude from infrared divergences, which we know very well. That's a very non-trivial thing that this result can be generalized, and we found an important connection between the UV and IR by inverse Laplace transform. And in fact, it turns that imaginary part of the amplitude would be when S is when the parameter S is large, will be inverse Laplace transform of infrared divergences, which may have different functional form. And finally, the amplitude and the limit when S goes to infinity and T goes to 0 will become not just a random function, but a function of T logarithm of S. For this conclusion, we need to assume only regularity of imaginary part of the amplitude and do some mathematics and some proofs that all the coefficients are positive, and we can make this procedure. And we noticed the funny thing that the Venezian amplitude for string theory satisfies this condition. If you expand it in powers of t, when t is small, then in S it will be an expansion. In fact, the leading term in S will have the form T log S.
In this analysis, are you assuming a square bound even beyond Planck scale?
Sorry?
You are assuming that amplitude is bounded by S square.
Yes.
And even beyond Planck scale.
Yes, kind of.
And so beyond that, I'm wondering if higher order loops will be relevant beyond Planck scale.
Higher order loops,
So
which
now
ones?
you are looking at one loop correction to gravity system.
One loop correction, you mean log t in the IR or in the UV?
Both in IR and UV. So in the previous slide, you were.
Yeah.
So here, A1 is associated to one loop.
Yeah.
And if you this is IR dispersion relation.
Yes.
And the next slide. This Z can contain higher loops as well.
This one?
Yes, in this expression.
No, I think it will contain extra. So here is this. That's why we fix it like arbitrary function f of t here, because it's the idea is that we can connect a given singularity in the IR. So we kind of go and ask people who are computing multi-loop in graviton scattering. I don't know if it was done at all, in fact. And then we can do inverse Laplace and get the imaginary part of the amplitude and the Ricci limit. And we get whatever we get. And this, so we did this procedure for 1 over t pole, the derivation of the result that it's a function of t logarithm of s. But in fact, this should be a subdominant term. So loop contribution look like subdominant terms to Ricci behavior. But it depends on what are the further loops. Maybe there are surprises. I don't know. We never have gone to more than one loop. So the idea is that we can reconstruct the whole amplitude under these assumptions, of course. We can reconstruct the whole amplitude also from imaginary part. And this is just knowing imaginary part of this form, we can write it like an integral of that. It's and by analyticity compute this amplitude and find actually this form. So that's the form of the amplitude and the limit t to 0 as to infinity, corresponding to 1 over t pole, like Ricci form of the amplitude, in fact. But we derive it in the way which is independent of concrete UV completion. So let me skip this slide. It's just some mathematical game. Talking about physics, at some point it was a big confusion in the literature about quantum electrodynamics with gravity. There is this kind of loop amplitude computed in the paper by Claudia Duram, Lasma Alberta, Sumer-Jaitley, and Anatoli. And they found negative coefficient in front of a squared and said that, okay, maybe this is bad for positivity. Normally it was, at that time, it was kind of a tradition to throw away graviton contribution, saying that it's gravity and it should be negligible in the IR, but it's divergent, so it's kind of, yeah, but the point is that if you use positivity bounds subtracting the graviton pole naively, you obtain that this contradicts positivity bounds, because second derivative should be positive, but apparently from this diagram it's negative. And there was discussion that the only way is to assume new physics at the scale of MMP. For electron it's 10 to 8 GeV, but then there was a discussion that maybe it's not electron but neutrino, and it's not photon but W boson. Then imagine neutrino mass here, and it's very low scale, something like collider scale physics. But this kind of story, in fact, really means the only thing that there are no positivity bounds with gravity for S squared term, speaking strictly. So this is not a contradiction and doesn't require any new physics at this scale. The reason is resolution of the paradox would be just that you can find a Regia form of the amplitude which will reproduce exactly the negative constant which you want. Any negative constant can be reproduced by assumption about UV amplitude. This form of amplitude in the UV doesn't contradict to any properties like unitarity, whatever. It's fine, it's absolutely fine, but if you plug it into dispersive relations, it will give precisely negative contribution, which will cancel the existing negative contribution. That's good to have this cancellation, but in fact it means that there is not just no positivity bounds can be properly derived if you consider seriously gravity for a squared term in the amplitude. So let me come to conclusions. UV and IR amplitudes are connected under the assumptions of unitarity, locality, and analyticity of the fundamental theory. Assumptions about UV lead to positivity bounds for infrared theory. Causality requirements does not lead to compact bounds, while the positivity bounds, all of them finally lead to compact bounds. The potential reason is that causality doesn't rely on any UV properties of the theory, and in particular, it knows nothing about Martin-Fourier bound, whether it's satisfied or not. So it means that causality bounds must be weaker than positivity in general, like looking at all-dimensional space of multi-dimensional space of Wilson coefficients. But in some slices, causality bounds are stronger than positivity bounds, if you just take some slices. So if we include graviton exchange, IR singularities in the forward limit allow to reconstruct forming the UV amplitude in the limit when t goes to 0 and s to infinity. And the particular, to be mathematically correct, it should be a limit when t log s goes to 0 and s goes to infinity. Gravity invalidates positivity bounds for second derivative of the amplitude, but still we can use bounds which are obtained from more derivatives of scattering amplitudes, like higher it's called dispersive relations with more than 2 subtractions. Okay, thank you very much. And this is a picture from near my workplace in Hangzhou Institute for Advanced Study. Just some backup slides. Okay.
I have just one comment about positivity in gravity. Can
Okay.
you go back?
Yeah.
2 slides. So here, actually,
The next one?
next one.
This one.
Later.
This one.
It's this one.
Okay.
Actually, but I have a paper with Jinsei, which tries to find so-called finite energy summary. And actually, by using this, we can give a bound on the second term, J. Bound on the amplitude. We can write down.
You mean this term?
Yes. Then we can write down this causal relation for the ridge amplitude, ridge parameter, and we can give certain bound. And then we can give a bound on the coefficient, which has to be small, which has to be bigger than -1 by Planck square and some certain energy scale.
Okay, so you can bound J from these bounds.
Yes.
Okay, yeah.
So we still have some hope to sharpen the bound.
I see.
Which we can.
But can you get like any bound for A double prime? Which kind?
Yes.
So you still get.
Yes, by giving bound on J, and then we can combine this with the dispersion relation for its square coefficient, then we can give a lower bound on A double prime.
So A double prime is larger than what?
Larger than -1 by Planck square times some energy scale, which is determined by the dispersion relation.
Okay, I see.
So still negativity is allowed, but we can give a bound.
So, but there is some negativity allowed at order Planck scale, right?
It is suppressed by Planck scale.
I see. Okay, yeah, I'll have a look. Thanks for the reference. I think I didn't read it carefully, at least.
Let me advertise it later.
Yeah, I definitely should. Okay. More questions?
Can I ask the question?
Yes.
You mentioned about spin-2 completion and also action completion, which is kind of partial completion.
Yeah, I mean, for completions, that's my backup slide. Like just what we mean by these completions is just the points in the space of these coefficients.
My question is whether we can distinguish between chain-through completion, UV completion, like scalar completion, and partial completion, like action and spin-2 completion.
Can we distinguish between full UV completion and partial? You mean this? Sorry, I didn't got the question.
So, if UV completion is by scalar, I think it's full completion. You don't have to.
This is not scalar QED UV completion. This is full UV completion. Yes. Well, up to Landau pole. Yes. All of them are really up to Landau pole, but it's a different story. Scalar by scalar, what means here it's just coupling. So axion coupling is phi over lambda f dual, and for scalar it's just the same, but f over lambda f minu. That's the definition of our scalar UV completion. It's a bit kind of. It's not a real completion. Yes.
So can we distinguish like scalar? Scalar and axion between scalar, scalar, vector QED?
Yes, there are different. You see this you integrate out electron and get this kind of complicated coefficients because you integrate out loop of the electron. And here you integrate out three-level exchange.
Maybe he is asking if we can carve out the parameter space, which is allowed by partial UV completion, but not allowed by free UV completion. I mean, let's see. Probably.
But you mean by full UV completion?
Yeah. So this scalar UV completion, the action UV completion is just partial.
Yes.
And he's asking if one can exclude some parameter space where partial UV compression realizes. But maybe if you take into account some further UV effect, there is some small tiny deviation.
Yeah, maybe, but in fact, well, what we observed is that both scalar and axion UV completion are living on the boundary of allowed region.
Yes, and
normally it means
if it is on the boundary, and
yeah.
if we can exclude this single point, then this means that the further UV compression should shift this boundary to inside, for example. This is what we want to ask.
I want to ask. Distinguish.
So, like, if we can exclude boundary, then we can say that this scalar UV compression is just partial and we need further UV compression.
I think it's it's a tricky question, but in fact, first of all, in this consideration, one should also add loop corrections, right? But the point is that loop corrections are not there for dimension 4 and dimension 6 operators. They're just no loop corrections to them.
So probably possible answer to it could be by considering much higher order terms.
Yes, it's much higher order terms.
Then
yes.
slightly shift the boundary inside.
I think it can be. I don't know actually. If you have just this particle, then I think that at least for where this point appears in the plots of between fourth and sixth order operators, I think this point is exact because there will be no loop correction, no log correction terms to that. So if I show again the amplitude, what I mean, we looked now at tree-level amplitude, but in fact, there are loop corrections known to that, and S squared and S cubed term, they don't get any loop correction. So G2, G3, H3, and F2 are exact, and F3 too. They are they do not run. They don't have running. So if we have plot where this point is on this slice, it should be an exact point. Unless there are some extra fields added and it's a completely different story, different theory. But in the slices where it's like G4 operator, then it's more subtle because G4 comes with a log term also. And we should be careful about that. Okay, more questions? I think next talk. Okay, thank you very much. I think we can go further.哎，喂，下一个有没有报告呀？下一个看一下，好像下一个没了吧？I think there's no until this 4 p.m. 4 p.m.
There is no talk now?
行吧，那我们就玩一会儿，然后那个4点钟开始。哎，你能不能问一下童心，能不能提前开始啊？
行吧，行吧。We start at 4.
The talk by Jia Liu was cancelled.
Actually, he want to change, but then 他刘佳不是说是改时间吗？他没说是那个要取消掉呀。啊，喂，有人在吗？不是，他好像是说他想排到周三，然后但是好像周三，就他之前跟我们说，跟你说了排到周三，但是没改，然后他就算了。行吧，行吧，那就对，可能你们，我是说你们都是扣奖的，就是一个公司的，就是为什么就是他改时间了，你们不知道。哦，行，没事，那我们就开始。哎，你我加了你微信吗？好的，好的，好的。
2011哦，背不得了，2014到2018，然后2018到2023在 HKUST 读 PhD， 然后现在在Cambridge 做博后，然后他会给我们讲这个correlators through the looking glass. Please use English. Sorry, my introduction becomes Chinese. Okay, let's start.
Okay, thank you very much, C, for the introduction. Everyone, I'm Xitong from Damping, Cambridge, and I'm very I'm very glad to attend this Chongqing workshop on cosmology and fundamental physics. And today I'm going to talk about cosmological correlate class. This is work based on this paper together with David Stefanesen in Nottingham University of Nottingham, and Yuhan Zhu, who was a PhD student together with myself in HKUST, and now is a postdoc in IB. So let's begin with this. I'm going to very brief introduction to correlators and what they are, what they do, and then to the topic of cosmological wave functions and introduce its analytic structures in particular, and see how this is related to parity in the early universe. And then we move on to the main topic of today, which is the reality and the factorization theorem. And we give summary and outlook in the okay. So let's begin with a brief history of time. And this is a classic picture of the evolution of the universe group. I was initially going to use this figure to illustrate how cosmological correlators can play a role in both primordial cosmology and late-time cosmology. But I realized that there's too much emphasis on the colorful in the late-time universe in this figure. So instead of using this plot, I'm going to try to use my own plot, which is less fancy but more to the point. So I'm going to define my time as a arrow upward. And in the beginning of the universe, we start with a big bang or a Planck year or something, and then it is widely believed that afterwards the universe goes through a period of fast exponential expansion called inflation, and then inflation heating, and then you start the usual hot Big Bang expansion of the FRW universe. When the universe expands, temperature could get the formation surface and the structure formation surface, and in the end, we are here today. When we look backwards in time by constructing large telescopes and do observations on the sky, we essentially see the history of the universe. What we found is that the universe, large-scale structure of the universe is approximately homogeneous and isotropic. And this is perfectly explained by this process of inflation because of the exponential expansion of space-time, spatial curvature is diluted, and the perturbations are also diluted, as well as the number density of monopoles, etc. Relics kind of provides a very good explanations for what we found in the sky at the largest structure, But if you look more carefully, you find that there's the temperatures and the density fields are not really homogeneous, and small random fluctuations at 5 at the primordial, and these are believed to come from the quantum theory inflation. These was the quantum fluctuations when they are stretched outside the horizon and decohere, become classical fluctuations that seize all the structures that large-scale structure. And since we have small random fluctuations locally on the sky, we can measure correlation functions. For example, this temperature of the CMB sky to the nth power. And from this these so-called cosmological correlators, we can infer of perturbations defined at the reheating surface, which were then evolved from an inflationary era that could possibly tell us the detailed physics inside the inflationary bulk. For example, the Lagrangian, the particle spectrum, the interaction type, symmetries, etc. So these cosmological correlators that we measure at the late-time sky is able to give us very valuable information about the inflationary physics at the primordial era of the universe. So what can we do with background? Also approximately, this is the slow roll tractor of small perturbations around this slow roll background by expanding the inflaton field and space-time dependent perturbation, as well as the metric, the spatial metric. You can define correlation functions of these perturbation fields, delta phi and zeta and gamma, and they have to be there because the theory is not a completely linear theory for perturbations. So you're going to get non-trivial correlations from the non-linearities of this single field slow inflation. And these are encoded in these correlators of massless fields. For example, curvature field zeta to the nth power times gamma ij, the primordial tensor fluctuations to some nth power. So this n plus m point, we use n plus m runs from 2 to infinity as an integer. And these correlators are defined at a time eta naught, where eta time at the when eta 0 approaches 0, defining this correlator as a spatial bound of inflation, the reheating surface. And this is the correlator introduced by Weinberg in 2000. So in this minimal simulation model, these correlators physics, the 2-point function is roughly given by phi dot squared. times Hubble to the 4th. So if we can make it squared, which we did, this should tell us of this rolling speed of it, which we now believe as 3,500 Hubble squares. So by measuring the power spectrum, and the power spectrum of the tensor perturbations gamma ij squared is roughly given by 8 squared over m Planck squared. Since we know the value of m Planck is something like 10 to the 19 GeV or so, 19 or 18, then by measuring a non-zero tensor power spectrum, we would get infer the inflation. From the 3-point correlation functions and on, these are all slow roll suppressed by the epsilon eta parameters, slow roll parameters of inflation. This gives us consistency checks of the single field nature. So one sees that one can there's plenty of information that are encoded in correlators of fluctuations during minimal model. Go beyond the minimal. For example, if you go to the of inflation first proposed by Trent to turn on opening of the fluctuations interpreted the tensor all couplings, the rotations, they are related to each other internally by the spontaneously broken time diffeomorphism. And this is a very general model. And in this set of parameterization of the effective field theory of inflation, the 3-point correlation goes like 1 over the sound speed squared. So by measuring these 3-point correlations, you get an information of the inflaton sound speed as well as the UV cutoff of the EFT of inflation. And one can even go more beyond this EFT of inflation by coupling the massless states, these zeta and gamma fields, to extra massive spinning fields. For example, I all labeled it by the sigma field. For example, scalar sigma or vector sigma I, tensor sigma ij, plus their interactions. In this so-called quasi-single field inflation model, if you look at the squeeze limit of the 3-point correlation functions, you find that there's a peculiar behavior, which is a factor that goes like the ratio of the momentum scale hierarchy to the some 3/2 power plus minus Im over h times PS cosine theta. So as you squeeze the momentum triangle, the correlation function actually oscillates with a frequency precisely determined by the mass of the exchanged signal particles. And the spin is encoded in the angular distribution, whereas S encodes the spin of the signal fields. So this means that this 3-point function in the squeeze limit is essentially acting like a cosmological collider that probes the particle spectrum of inflation. For example, the mass, the spin, the sound speed, the chemical potential, etc. And this is a very interesting paradigm, because if we can somehow probe particle physics through this measurement of the cosmological correlators, we would be able to achieve a collider at a scale of, say, 10 to the 13 GeV or so, which is considerably larger than any terrestrial collider that can be envisaged in any foreseeable future. So now we see that the cosmological correlators are wonderful probes of the primordial universe, but the question is, can we detect them? Well, what we do know now from Planck 2018 is that we have measured a curvature power spectrum, which is the zeta squared equals to 2 times 10 to the minus 9, the famous Kobe normalization, as well as its spectral tilt and the running of the spectral tilt, etc. There's a nice plot of power spectrum as a function of K. It's Planck paper. However, there are plenty of things that we don't know. For example, the tensor power spectrum hasn't been detected yet, but it has been constrained to be smaller than 10⁻⁻10 by Planck 2018. We haven't detected any primordial non-Gaussianities yet, which are correlation functions with powers of fields greater than 3. But there are also constraints, for example, on the scalar bispectrum and scalar trispectrum by the Planck collaboration to be smaller than some order 10 and order 10,000 numbers. However, there's still a bright future for cosmological correlators. For example, if you look at the future observations that probes the tensor power spectrum, you see that there can be a factor of 10 to 100 improvement on the so-called tensor to scalar ratio. Basically, is a measurement on the tensor power spectrum by the Simons and the CMBS stage 4 and the very futuristic PICO experiment. On the other hand, there is also a factor of 10 to 100 improvement on the primordial non-Gaussianities by various future CMB observations and large-scale structure observations. And the similar story is for the tri-spectrum curvature perturbations as well as the mixed bispectrum, etc. So we do see that there's lots of effort going on in the observational frontier. How about the theoretical frontier? Well, the theoretical frontier is all about computing and studying the properties of these endpoint correlation functions of massless states in inflationary space-time. And basically, there's a very challenging aspect, which is doing lots of complicated time integrals. And in order to overcome these difficulties, there's really a lot of efforts going in this direction of understanding the structures of endpoint correlation functions in inflation. For example, I listed some of them here. You have the bootstrap equations that turns the correlation functions, the integrals inside into a partial differential equations. You have the unitarity and causality cutting rules, and you have the constraints from bulk locality. And you can also view this whole correlator as some geometrical objects of as the so-called cosmological polytopes. And these polytopes enjoy a kinematic flow. And you can also go to Malin space and study the analytic structure of the Malin transform of the correlators. And you can, for loop level diagrams, you can use the dispersion relations to give analytical results for a certain class of bubble diagrams. And there are also numerical codes for efficiently computing tree-level diagrams at a non-perturbative level. So one sees that there's still plenty to learn yet about the theoretical frontier for the cosmological correlators. But the question is that we would like to understand how are the analytic structures of correlators reflected at an observable level. And in order to partially answer this question, we need to go further afield in this wave function formalism. So before I do that, let us look at this inflationary part of this evolution history of the universe that I drew previously. Here you have inflation, you have some spatial correlation functions defined at the radiating surface. I'm going to do a further simplification that turns in this illustration into actually a Feynman diagram. So on the vertical axis, we still have the time. This time is precisely the conformal time. And this horizontal black line represents the end of inflation or the reheating surface. And we approximate the inflationary space-time by a de Sitter space in the Poincare patch. So this black line would become a de Sitter boundary, a future boundary of de Sitter. And in the bulk where eta is negative, runs from -infinity to 0, we have the de Sitter bulk. And you can imagine there are some interactions, couplings, nonlinearities happening in the bulk. And in the end, they are characterized, they're encoded in the spatial correlations defined at the boundary. And in order to understand how these nonlinearities happen as a result of this unitary evolution, we can evoke a notion called the wave function of the universe, which is basically the state of the universe projected onto a given field eigenstate, a set of field eigenstates at this future boundary of de Sitter at eta naught. Sorry, eta naught is basically 0 here. And in quantum mechanics, we know how to compute the transition amplitude from the initial time to late time. It's basically given by a path integral of the e to the is, where s is the action of the whole theory, and you have to integrate all the field perturbations given the specified Bunch-Davies initial condition at past infinity and the Dirichlet boundary condition that you impose at the future infinity, future boundary. And I should notice, I should note here that this d phi in principle encodes all the all the perturbations in the field. So it's not this is in a sense different from the true wave function of the universe in the, for example, in quantum cosmology sense. So we are only integrating over small perturbations of fields here. So we're not, for example, changing the geometry, the topology of space-time background. We're basically just considering small perturbations and how these perturbations evolve according to the path integral. So some people would like to call it a field theoretical wave function. As soon as you get the wave function from doing the path integral, given an action, you can obtain the cosmological correlators by performing the Born rule. Basically, you square the wave function, you get the norm squared times the observable that you want, and then do an integral over these all possible values of the field that you get. So this is nothing but the good old quantum mechanical average value that we learned in undergraduate. But it's just now that instead of integrating over position psi squared, you get an integration over the field space of all possible field configurations that you have at the future boundary. And more precisely, one can define a perturbative expansion of the exponential of the wave function that takes this form. So basically, you exponentiate the sum of all the endpoint polynomials where n runs from 2 to above, and you have this delta function encoding the fact that you have momentum conservation because of spatial homogeneity or spatial translation symmetries, because that tells you that momentum has to be conserved when you go to momentum space. And the important thing is this psi n coefficient. This is called the nth wave function coefficient. Sometimes I also call it just simply wave function, but it is a function of the momenta of these external fields, phi k1 to phi kn, as well as the internal momenta and their norms. So this K without the black bold font is the norm of the vectors here. So this is our wave function coefficient. And as soon as you know these wave functions coefficients, you can exponentiate to get psi, and then you do the Born rule, you get the correlators. And so how do we compute this psi n? The psi n's are usually perturbatively computed by doing Feynman diagrammatics. For example, a generic diagram can look like this. And it's given by by assembling all the ingredients and then performing all the time integrals at all the vertices. So, for example, we have all the internal propagators, internal lines. By internal line, I mean a line that's not connected to the future boundary. So I denote them by a blue line here. Corresponds to GE, the so-called bulk-to-bulk propagator. And all the lines in red are lines which are connected to the future boundary. They are this K factors. They are the bulk-to-boundary propagators. For each vertices, you can have some derivative structures encoded by this D operator. And at each vertex, you have a vertex time. You have to integrate all the vertex time from -infinity to 0 to get the final result for the wave function coefficient. So this is basically the Feynman rules that you need to compute psi n. More details, the bulk-to-boundary propagators are given by this particular combination because, well, phi is the solution to the equation of motion of this field. So K actually solves the homogeneous equation of motion, and it's typically given in terms of the Hankel functions or the Whittaker functions, depending on your the linear dynamics of the theory. The bulk-to-bulk propagators, on the other hand, is a time-ordered combination of the bulk-to-boundary propagators. And these G solves the inhomogeneous equation of motions, basically the delta source equation of motions. And the vertex operators can be generically parameterized by some tensor structures of time derivatives and spatial derivatives. So in momentum space, it just becomes some vector structure, and you have to contract all the indices appropriately. And the power of scale factors is determined by diffeomorphism invariance in the theory. So how many derivatives you have to subtract the corresponding numbers of scale factors in front. And so these are basically all the ingredients you need to compute this wave function coefficients and finally to the correlators. One thing that I would like to mention further is that these theta functions in the bulk-to-bulk propagators are really complicated time integrals that becomes very difficult when you nest them to give rise to a diagram. Let's see an example of this wave function. So if I consider a topology that with an S-channel exchange here, and I'm considering a massless lambda phi prime q interaction example, this is a 4-point wave function coefficient. So I should write psi 4, and it's equal to the left-hand vertex acting on the bulk-to-bulk propagators, so bulk-to-boundary propagators with 1, 2, and the corresponding one on the right, and connect them by a bulk-to-bulk propagator GS in the middle. And then I do two time integrals. And after you do some tedious calculations, mathematical calculations, you find this result, where these K's without the black font are all defined to be the norm of the corresponding vector. And KT and EL, ER are the combination of the total momentum size summed together, as well as the partial momentum length summed together. And S is the momentum of the exchange state. And if you spend 1 minute to stare at this result, you find that there's some structure hidden in this psi4. For example, there's a 1 over kt to the 5th power in this expression, and that means if you analytically continue all the energy variables by letting kt to approach 0, but without approaching without sending all the k's to 0. So this means you have to do analytic continuation. You find there's actually a 5th order pole in this wave function coefficient. This is a so-called total energy pole. And the KT is also called the total energy because it's really the total energy flowing into the diagram. And in addition to that, you also get partial energy poles where when this EL and ER variable goes to 0. So you have some 3rd order pole factorized going on here. And so these are the singularity structure of the psi4 in this simple example. And one very important thing is that the total energy pole part is non-factorizable, whereas the rest of the terms are factorizable in the sense that this blue term can be written as a function of 1 and 2 on the left and 3, 4 on the right. So it's basically, they are independent of each other for this K1 and K2 energy variable. However, the total energy pole is not factorizable in the sense that the KT is a sum of K1 plus K2 and plus K3 and plus K4. So there's no way that you can separate 1, 2 from 3, 4. So I would like to emphasize that all the total energy pole pieces are intrinsically non-factorizable. This will become very important later. And another observation that we made is that the factorized part is relatively simple because you can when you have the privilege of writing something into a product of independent elements, you always reduce the complexity of the expression. And the last observation that I would like to make is that the whole thing is purely real. There's no complex number inside. Everything is purely real. And why do I need to emphasize the reality of this expression? Sorry, are there any questions?
Yes.
I have a related question to the third comment. So the factorizable part is not analytic with respect to S squared.
Sorry, a square?
So probably you are saying that factorizable part has an imaginary part. And relatedly, this part is not analytic with respect to S squared, like an intermediate momentum.
Oh, I think that that's very good. I think I'm going to talk about that later.
Okay.
That's important. Actually very important.
Thanks.
Yeah. Well, at least for this example now, this is the precise relation, and everything is purely real. But more generally, we will come to that. So why do I emphasize the reality of this thing? If we go back to the dictionary between wave functions and correlators, basically doing this Born rule, you find basically a map that takes you from the wave function to the correlators and vice versa. This is, for example, given in the Maldaceni's classic paper about non-Gaussianity. You find that there's real parts everywhere. There's always a real part accompanying every wave function coefficient in the dictionary. So that means only the real part of the wave function can enter the game of cosmological observables. All the imaginary parts are just purely phases of the wave functions, and then these phases get lost when you do the absolute value squared. So that's why reality is important. But is it really true that only the real part can enter cosmological observables. Actually, we need to notice that we're now in momentum space. In momentum space, when you do a complex conjugate, the conversion quantity e to the ikx becomes e to the minus ikx. So one has to be careful when you do the norm in momentum space, because you would need to flip the momentum at the same time. So instead of the previous dictionary, I should really write a new dictionary where I replace all the real parts by something I define as the parity real part, a PRE, where PRE is given by psi n plus psi n star with minus k. So there's actually a parity transformation in the second term. So that's why we I put a P here. This is actually the correct. I should say complete dictionary between wave function coefficients and correlators. So now you see the reality is tightly related to parity in momentum space. Because if the whole theory is parity invariant, I can just drop this minus k because everything is parity even. Then I just go back to the previous expression, and only the real part of the wave functions contribute. But in general, if you have a parity violation, not only the imaginary part, we're going to enter observables. Well, speaking of parity, it's actually an old friend in physics. As far as I know, it's first introduced by Wigner in quantum mechanics to this space-time transformation that reverses all the spatial directions. And we know that it is an exact symmetry for classical mechanics, Einstein gravity, and quantum electrodynamics. But we know it's not respected by the microscopic electroweak theory, and this is famously proposed by Li and Yang in 1956, and then was quickly was soon by the Wu experiment at the same year when she looked at the cobalt 60, and afterwards it just becomes a frequent routine that parity is violated in the microscopic description of the standard model of particle physics. So we know that parity is indeed violated at small scales. Natural it's actually natural to expect that there might be some parity violation at the cosmological scales, because the expansion of the universe brings small things to big things. So if there one can imagine that if parity is violated at small scales, the expansion of the universe would bring that small scale parity violation physics out to a large scale. So large scale structure can indeed originate for small scale physics.
Hello?
Yeah.
I wonder where's the boundary of this violation?
The
Violation, the boundary, like just this 10 to the minus 20, or we don't know.
Oh,
I mean, do we know the boundary of that?
well, I think there's no
Physics cause result in terms on the right. Also, that does that exactly match?
I don't. I mean, one should that there between us.
No, not that. Cosmology we correspond to at the cosmological scale.
Yeah. There's definitely some correspondence between the spatial scales and the time scales there. Yeah, that's to be sure.
But we don't know the exact boundary on both cases.
No, I don't think so.
Maybe is that a gradual change?
Yeah, yes, it's a gradual change. I mean, it doesn't have a sharp boundary, but
okay.
yeah, but it might be some say extension. So say from 10 to the minus 19 meters to well, if you go back to the energy scales, probably is coming to some 1 TeV or so, and then you get another order of magnitude on the other direction. You can also map this to the time, cosmic time, etc. But it's a smooth process.
You can go all the way to Planck scale.
Yeah, I mean, this dictionary is between space and time and energies is always the same. It's always there. That's always the case. Yeah.
Okay.
Okay. Right. So speaking of parity, how do we measure it in cosmology? Of course, in cosmology, we have these primordial probes of parity must be encoded in this tensor and the scalar fluctuations that we had. In the tensor sector, parity is actually sensitive at 2-point level, because at 2-point level, you have a momentum defined by the separation of 2 points, and you also have a spin vector characterizing the spin of the tensor field. So by forming these two vector and a pseudo vector together, this combination is actually sensitive to parity. So you can basically detect parity violation at 2-point level. This is, for example, the case when you measure the primordial tensor power spectrum. But in the scalar sector, it's actually 4-point sensitive. So you really need to go to 4-point or above to see parity, because for 3 points and 2 points, the kinematic configuration is exactly planar. A planar configuration can always be brought back by rotation if you do a parity transformation. So as long as you respect spatial rotations, parity must be encoded in at least 4-point correlation functions of scalar fields. And this is actually also our main focus for today. So how do we define these parity odd correlators from inflation? So this zeta n parity odd part can always be defined by this original correlator minus its parity inversion, where I flip all the external momenta. And then we can imagine that it can come from inflationary processes that I include in the blob. However, there's a no-go theorem initially established by me and my collaborators, and as well as generalized by lots of other authors in a recent paper, that basically says that there's no tree-level parity violation in single-field slow rate inflation. And in order to bypass the go-no-go theorem, you really have to look into either the loop process. You have to break scalar invariance or Davis vacuum state, or more naturally by adding extra. But then the question becomes, can we dig deeper into the universal analytic structure of the parity autocorrelators? Because we saw previously that there is some universal analytic structure in the wave functions. How much of these structures survive in the parity autocorrelators? And the second question is that, can this universal structure help us to simplify the computation? Because you remember these theta functions will cause complicated nested time integrals, and we don't like to do that. Can this structure simplify that procedure? Well, in order to answer these questions, we have to stare back at our parity autocorrelators defined in the previous slide. We realize that zeta is actually a Hermitian operator, a real operator in position space. But if you Fourier transform a real operator in position space to momentum space, it actually becomes complex in general. And interestingly, a complex conjugate in Fourier space, in momentum space, exactly maps you to the parity inversion of the field in momentum space, a Hermitian operator in momentum space. So this means that the parity odd part of the correlator, so this should be zeta to the nth power, so all the nth power correlation functions this apply, it has to be purely imaginary, just by this simple argument. So any Hermitian operators, the parity order of the Hermitian operators correlator must be purely imaginary. And that's also reasonable because we know that the world through the looking glass has to be imaginary. So parity autocorrelators must be purely imaginary, or one can rephrase this statement as that any real terms in the wave function never get into the parity odd component of the correlators. So if we encounter some real terms in the wave functions, we can always just drop them. They don't enter into the game in the final result. So how much of the wave function is real? Well, in order to answer that, we have to look back at our perturbative expression for the wave function coefficients. They are again assembled by putting together bulk-to-bulk propagators and bulk-to-boundary propagators with a bunch of derivative vertex operators. And these bulk-to-bulk propagators introduce complicated time integrals by these theta functions. They are complicated to be computed, but really, before one asks how to compute these complicated nested integrals, one has to ask, are they really needed for parity autocorrelators? Because as we mentioned before, anything real doesn't really enter into the final result. So if these complicated nested integrals are purely real, we can just drop them. That's actually indeed the case. In order to see that, let's do a clever trick, which is by performing a Wick rotation. Wick rotation takes you from the real conformal time to a purely imaginary conformal time in the upper complex plane. And under the Wick rotation, all the bulk-to-boundary propagators become purely real because they're basically just polynomials times exponential functions with arguments that always comes with an I eta. So after Wick rotation, it just becomes purely real. This is assuming Bunch-Davis vacuum. Of course, if you have non-trivial vacuum, this is no longer true. And the vertex operators are also purely real due to scale invariance plus unitarity. Unitarity just basically says that couplings are purely real. Otherwise, the interacting Hamiltonian wouldn't be Hermitian. Now you recall that the endpoint wave function, actually the tree-level endpoint correlation wave function, is given by this assembling of vertex operators and propagators. And you see that D has become purely real. K has become purely real. The only thing that we are not sure of is this bulk-to-bulk propagator. We need to check its properties. However, after you do the check, you find that the bulk-to-bulk propagators are not in general real after weak rotation. But if you look at the definitions, how do we define a bulk-to-bulk propagator? The bulk-to-bulk propagator must solve the point source equation of motion. So here's the equation of motion for a massive field phi, scalar field phi with a delta point source. And the way the equation of motion itself after weak rotation, you see, is purely real. Nothing is imaginary here. Nothing is complex. The boundary conditions at infinity, which is the vanishing boundary condition, is also purely real. So that suggests that there at least exists a solution of G tilde, which is purely real. And any other solution which differs from that can be accounted for by adding appropriate homogeneous solutions to the homogeneous equation of motion, which are factorized intrinsically. This motivates us to do a so-called CF decomposition. Basically, we decompose the original G tilde, that is bulk-to-bulk propagator, into a connected part and a factorized part by adding and subtracting a term called delta G phi. And the delta G phi is chosen such that the connected part C is purely real after weak rotation, and that it converges in the infinite past. And after we do that, and we go back to the perturbative expansion, you see that this D has become real, K has become real, G has become a sum of C and F. And the C is the connected part, and we have chosen this part to be purely real. And F is well, complex in general, but it is factorized in the sense that it doesn't contain any time-ordered theta functions. So you can just expand this whole product and take what we call the maximally connected piece, so the piece with the maximum number of C's, plus other factorized contributions. So these factorized contributions will have less time ordering integrals that you have to do. So they are, in a sense, simpler. And what this means is that the maximally wave function has to be purely real, because every ingredient in the expression is purely real. Yeah.
Yeah. So then the point here is to prove that this F tilde should all be factorized.
Yeah. They are factorized by construction.
Yeah. Could you go to previous? Yeah.
Yeah. For example, F is here. Is
I
factorized.
didn't quite follow this composition.
Yeah. So the C part is original. Yeah, this part is the phi member part, right? This is the Schwinger-Keldy's propagator.
So you on the propagator level, you can already see it.
See the fact that it is factorized. Yeah.
Yes. Yeah. Does that factorize correspond to some real particle production kind of thing?
That's a good question. I'm not sure about that. Because the C part also contains cosmologic rider signals, I think. It contains I think it's the local part.
I remember you do something like that before.
Yeah, that's a very good point.
Is that the same?
Yeah. Our old cosmological cutting rules for cosmologic rider signals actually motivates us to do this decomposition. But the original rule doesn't apply, because if you do now is actually, we understand it as a causality cutting rule. That cutting rule brings you to a non-bunch Davies initial condition. So basically, it brings out the negative frequency contribution at the infinite path. So the result you get wouldn't converge. So that's why we choose another decomposition. But that's exactly what motivates us to do this procedure.
Oh, okay.
Yeah, maybe we can chat afterwards about that.
Okay.
Yeah. Okay, so now we have established that the maximally connected wave function is purely real.
Can I ask a question?
Yeah, sure.
Now I want to come back to my previous question, and this F is the non-analytic piece associated with on-shell particle production propagator.
Yes.
Okay. Good.
Exactly. Yeah, F encodes some information on particle production, but as I mentioned before, the C actually also contains a bit part. So it's safe to say that F contains particle production, but it's not safe to say all the particle production information is inside F.
So yeah, for example, when we consider flat space propagator,
Right.
we can decompose it into a real and real part, which is principal value
Yes.
of the propagator, and
Yeah.
we have imaginary part. But this F is different. It's not necessarily the same as this imaginary part. Is it exactly the same? Or?
Right. I should say this. So G is in general complex, so it has a real part and imaginary part. But after this decomposition, C is purely real. So that means all the imaginary parts goes into F, but there are also some real parts which goes into F.
Yes. And you said there are some particle production type, on-shell particle production type contribution in the C part also.
Yes.
And how should we interpret this particle production?
This actually brings up to the the good old the old cutting rule thing, because there are essentially different types of cosmological collider signals. One type is like from spontaneous particle production via the Bogleubov transformation. That part is indeed only inside F. But there's another piece of cosmological collider signals which comes from vertex particle production. So, because of the fact that the vertices are non-Gaussian, so you have this. You can imagine that at some point this vertex just pops out 3 particles, something like that, and that part is still inside C.
I see. Thanks.
Yeah. Thank you.
Then why does this called the total energy reality theorem? It seems that you just
that's exactly my next step. Well, because the maximally connected wave function is purely real, and we know the factorized part. We know that total energy singularities cannot be factorized. Therefore, the total energy singularities must lie within psi and C, the maximally connected piece. But because the whole thing is purely real, so all the singularities inside must also be purely real. Okay, this is the logic flow. Because the KT poles cannot be infactorized, then it must be in this piece. This piece as a whole is real, and the singularities inside must also be real.
This is the KT. KT cannot be factorized. Because if it factorized, then there's one of the KT cancel, like.
Well, it's just related to the fact that 1 over KT cannot be written as a factorized contribution from, say, some part of the external momentum and other parts. Right. The fact that the sum of all the external energy going to 0 is a non-separable thing.
Okay.
Yeah. So that you have the imaginary part of the residue of this thing has to be 0 for all the powers of K. And we generalized this statement basically to theories with any mass spin, sound speed, and chemical potential. for any massive spinning fields inside this ether, as long as it forms a tree diagram. So
Sorry,
it is true that, yeah.
Any mass, any what?
Sorry?
A mass, spin, sound speed, chemical potential, like a spin half.
Spin. Oh yeah, that's a good point. So we're only considering bosonic fields. So because if you consider, say, fermions, you have to consider loops. Yeah. So
But
here we're considering
it
trees.
may be applicable to loop level.
Yeah, that's another good point. As far as we know now, we know there are counterexamples. So it's not true for loops.
What example?
Well, actually, this the work done recently by Enrico and his student Chiara and Gordon. So basically, you can generate a parity violation from loop diagrams, and in the final result, there is a KT pole.
Okay.
It has something to do with the rotation of the integral measure. So instead, I mean, on top of these DKGs here, you also have to rotate the integral measure, and there you have some extra pieces which has an imaginary part. That brings out the KT poles out. Yeah. If you're interested, we can chat afterwards. Yeah, so this is basically the main result of my talk today, that tree-level parity correlators cannot have total energy singularities. They must be factorized, and because of that, they're easier to compute than naively expected. An example at 4-point level is that, so you remember this parity structure for 4-point level, and in diagrammatic language, it basically forms a connected psi 4 plus a psi 3 bit, and psi 3 bit is just always there. It's factorized, so easy to compute. I just leave it here. But the connected piece, you can use a CF decomposition to write a C contribution and F contribution. And the C contribution drops to 0 because of the reality theorem. And then you see that all the parity correlators at tree level at 4-point are just given by these two contributions. And therefore, their general structure is just a sum of some coupling constants times kinematics times a hypergeometric function of the left variable times the hypergeometric function of the right-hand side variable. This is true for any spin, any mass, any chemical potential, or any integer spin, any chemical potential inside for the exchanged field. And we applied this factorization theorem to the spin 1 case with chemical potential, and we found a perfect match with a direct and numerical integral. So these data points are from numerical integration, and the red line is our exact result of this form. So you see that they typically match very well.
Spin 1 chemical potential. You said you already prove it for whatever chemical potential.
Yeah, so this is an example, right? So I just use it to check that it is true, that is correct. Because this is the first analytic result for this model. Previously, we didn't know the precise.
Actually, what about the? I mean, actually, I didn't follow up this chemical potential thing, and you done it for spin 0, 1, and 2.
For us, it's like spin 1/2 and spin 1. But I mean that's actually tangent to the topic here. If you are interested, we can talk, probably chat out probably afterwards.
Okay, so continue.
Yeah, here I'm just picking up this particular example because we did, for this example, we didn't know the precise result. We actually did some approximations using the so-called non-local EFT or partial EFT to treat the system. But you see that in some parameter spaces, there are still some mismatches. But now we really have the precise formula due to the parity or factorization theorem. It's a perfect match with numerics. So we're kind of happy with that. That brings me to the summary, that cosmological correlators are crucial probes of the early universe, and they are better understood in terms of analytic wave functions. The analytic structure of wave functions links reality to parity. And then by using unitarity, scale invariance, and Bunch-Davies vacuum, we derived the total energy reality theorem, which states that all the total energy poles in a wave function are purely real. Under parity, this becomes the fact that all correlators at tree level are factorized. And there are also a few outlooks, for example, going into loops. How can we modify this relation, this theorem? And also, is there a Kramers-Kronig analogy? Or what is the perspective from Euclidean ADS? And how to classify these total energy singularities, etc. That's basically what I have to say today. Sorry for overtime.
Thank you.
Thank you very much.
I have a question about observation.
Yeah.
So you said your motivation is partially in the recent kind of potential detection parity violation in trispectrum. And suppose that this has a primordial origin, and is it consistent with constraint coming from CMB? Like a
yeah, that's a very good question. As far as I know, there are some tensions between CMB dataset and the large scale structure dataset. So basically, people found no obvious signals of parity violation on the CMB dataset, which is like a more controlled, more controlled dataset, because there are lots of unknown stuff going on the large scale structure side. So yeah, there are some people don't believe that the large scale structure parity violation is like is like correct, or is not really as significant as that, because there's a huge systematic uncertainties in the covariance matrix. I'm not an expert in this field, but what I heard from people is that there's some tensions between these two data sets, and people tend to think that the CMB is like a cleaner understanding. So it's probably something we have to check at the large scale structure side.
Okay, thank you.
Yeah, no problem.
I guess there's already, is there more questions from online?